good. Okay, now we're recording. So anyway, and I believe that is actually on the, that's on the previous slide, that for these standard potentials, concentrations have to be 1 molar, temperature has to be 25 degrees C. So everything in the table should correspond to that. And then when you're doing a calculation, all your concentrations have to be 1 molar, and your temperature that your cell is operating at needs to be 25 degrees C. If it's not, then we have to correct for that, and that's what our next slide is about, the Nernst equation. That's what you're going to do if your concentrations are not 1 molar. And in fact, we've got 2 versions of the Nernst equation. This is the first one right here. And the Nernst equation will be given on any exam. No one ever expects you to remember this thing. This first version of the equation is for if the temperature is not equal to 25 C. And the concentration, so that's going to be, it's going to, in this equation, it's reflected in Q, which is a ratio of the concentrations. But anyway, the concentrations are not 1. It's something different. So anyway, this first equation, that's what we're doing here. So R is the gas constant, T is your temperature in Kelvin, and then F is Faraday's constant, N is the number of electrons that are transferred, and then Q is a ratio of the concentrations. Or it's, we did this before, it's a reaction quotient. So we've got the equation for doing that. It's the products over the reactants, where the products are the reduced version of whatever it is divided by the oxidized version of whatever it is. Okay? And for some of those, if they, for a lot of the reductions, one of the materials is a solid, therefore its concentration is going to be 1, and the oxidized form is going to be some other number. So it's usually going to, for those, it's going to be the reciprocal of the concentration of the oxidized. Now, thing is, we're not really going to do any problems with this first equation, but I wanted you to see it before we get to the equation that we're really going to be using. So I'm going to erase everything now, and I'm going to go down to this equation. Oops, the one below. And it will also be provided. So you're not going to have to remember this. But this equation is a lot simpler because, some things are just not there. No gas constant, no temperature, and no natural log, or not natural log, no Faraday's constant. But N is still there. So all of those ones that were taken out, those are all reflected in this value right here, the 0.0592. So that's making up for everything we got. We still have N, and we still have Q. So now let's see how we actually use this thing. We've got an example equation here, and we've got oxygen. We got, boy, it is morning. We got iron 3, and it's going to get reduced to iron 2. So we're going to add 1 electron to do that. And if the concentration were 1 molar, it would be that value. That would be if the concentration of iron 3 and the concentration of iron 2 were both 1 molar. We'd be using that number. But if they're not, then we have to use the Nernst equation to correct for it. And that's what this down here is telling us. The concentrations are not 1. The iron 3 is 2 molar, and the iron 2 is 4 molar. So they're different than 1. So you're going to take those two numbers and put it over here in order to get a value for Q. Now, to know what's going to go in the numerator and what's going to go in the denominator, we go back up to here and we follow the usual pattern for equilibrium constants or reaction quotients. That is, it's going to always be the product over the reactant. So for these reductions, the product is whatever it is reduced, and the reactant is whatever it is oxidized. So for our equation, and I think I'll erase and get a clear sheet here, our reduced form has only 2 positive charges. So that's the Fe2 plus. And the oxidized is 3 positive. So the iron 2 plus is the product. So that's going to go in the top, or the numerator, of our fraction. And we get that from here, where they told us that the concentration of the iron 2 is 4 molar. Excuse me. And then our oxidized form is the one with a greater positive charge, the 3 plus, and its concentration is given here as 2, so that's where this 2 comes from. And so you're just dividing 4 by 2 and you get 2. And that then is the value that is going here. That's what you're going to take the log of. Now the other thing we have to do is figure out what N is. So let me erase again. We need to know what the N is here. Well, the N is the number of electrons that are getting transferred. So if we look at the balanced equation for this, it's only 1 electron. If it was a greater number of electrons, there'd be a coefficient in front of the E. So that's why down here, what we're putting in for N is 1. And so, of course, taking the 0.0592 and dividing it by 1, it's still 0.0592. And the log of 2 is the 0.301. And the 0.77 is what the reduction potential is if the concentrations were all 1. So then we just combine all this and simplify it. And now the potential is 0.75 volts. So the value up here where the concentration was they were all 1s, is now 0.75 when the concentrations are 4 and 2. So that's how you use Nernst equation. Has anybody got a question on that? Okay, I got a worksheet I want you guys to do. I'm going to put you into your groups and have you do that. Let me show you the worksheet. And it says determine non-standard potential for the reaction. And we're just using the same reaction, the iron 3 going to iron 2. So its potential is still 0.77. The concentrations are iron 3 is 3 molar, iron 2 is 9 times 10 to the negative 5 molar. Here's the Nernst equation. It's given. If you need to see this after I put you into groups, you can get that at Blackboard. Let me show you how. So to get to the worksheet, you would go to course materials, and then you would go down to worksheets, and then you'd go to the worksheet for worksheets for electrochemistry, and this is the one you're needing, Nernst equation. So you click there, and there's the same worksheet. That's how you get it once you're in your groups. Everybody good? Anybody got a question? Okay, let me make sure that there hasn't been someone else join us that needs to be put in a group. Yeah, I got a couple people, so let me take care of that. And then I'll push the start and you guys can figure out the answer. Okay, I got everybody in what ought to be their groups. If you guys have a question or if I put you in the wrong group, send me a chat message, okay? And I'll take care of that. And, okay. Everybody's good with this apparently, so I'm not gonna worry about it. We'll move on to something else. Oh, what's going on with this? Oh well, never mind. Okay, so let's get back onto the lecture part, onto the PowerPoint. So we just did Nernst equation. You guys saw it on the slide and you did it on a worksheet. And like I was saying in the chat, you'll have the equation. So all you got to do is figure out, what's the value of n and what's the value of q. And if you got those, then you're good. So otherwise, it's not a big deal. Okay, so now we're going to make a change here. Up to this point, we've been doing voltaic cells. So for this cell potential here, we were looking for a situation where the result was positive. So this is for voltaic, or they also call it galvanic cells. So make that bigger. So this is all for that kind of situation. So voltaic or galvanic, you get a positive value. But we're now going to go to what the situation is when it's not spontaneous. It's not going to spontaneously produce a voltage. In fact, it's going to require us to apply a voltage to cause the process to happen. And instead of being called voltaic or galvanic cells, these are going to be called electrolytic, or we just call the process electrolysis. So this is not the removal of those persistent, hair growth that you don't want. That's a beautician kind of a thing. Aren't you glad I brought that up? Anyway, no, this is something different. Same word though. Anyway, in this case, if you were to try to measure the potential, it wouldn't be positive, it'd be negative. The electrons would be flowing in the opposite direction normally. But we're going to apply a voltage source that's going to force the electrons to go from the anode over to the cathode. Okay, so this example here, we've got molten sodium chloride. It's at 800 degrees C. And this picture is a little hard to get because there's actually a line coming across here. And below the line is all molten. But yeah, you can't see it very well. And then what's happening at the oxidation side over here at the anode, the oxidation, the chloride from sodium chloride is being converted into chlorine gas. And so that's our green bubbles here. We can collect the chlorine gas and we can sell it and make money. Yay. Anyway, if this was a reduction, which it's not, it's an oxidation, its potential would be a positive 1.36. Since it's a oxidation, it's actually negative of that. And then on the other side of our cell at the cathode is a reduction. We're taking the sodium cation, Na+, and we're making it into sodium liquid because it's liquid because we're still at this very high temperature of 801 degrees. I mean, sodium's normally solid, but since we're heating it up a lot, then it's going to be a liquid. We can then collect that liquid sodium and let it cool and make bars of sodium, and we can sell that. So we could take sodium chloride, water, and we could then do electrolysis, make two products that would have commercial value: chlorine gas and sodium. This time for the salt bridge, instead of a tube between the two, we've got something they're calling it a porous screen. So this is probably a ceramic material that has small holes in it, very small holes. And so that allows the ions to be in balance between the two sides. So anyway, that's one example of electrolysis. Another example is what we have here. Notice again, you have a voltage source. We're not measuring a voltage, we're applying a voltage so that we can then force these reactions to happen. So we're starting with water, and we're going to take the oxygen from the water, make oxygen gas. We're going to take the hydrogen from the water. We're going to make hydrogen gas. So you can see those bubbling up in the water, and then we're collecting those. And when we consider the formula for water, you've got twice as much hydrogen as you have oxygen. So that's why you can see that we have displaced the water to a greater extent with the hydrogen as compared to the oxygen, because there's just going to be more hydrogen molecules, more H2s than there will be O's. And this is used, let's see, the one place I know where this is done is that we take water and we want to produce oxygen, and that's done on submarines because they got plenty of water, and so they can use that to produce oxygen for the crew. And it's also done on the International Space Station for some of the oxygen that they breathe. They'll take some of their water storage and convert it into oxygen, and then they don't use the hydrogen for anything. They throw it away. At least that's what they were doing while I was still working there. It may be, I know they were going to possibly start using the hydrogen, and they were going to make, what were they going to make? They were going to make a fuel that they could use for the orbit, to maintain orbit. But I don't know if they actually went ahead and did that. So anyway, that's the two places I can think of where this process is actually used. I don't think it's really used that much, other than for some odd applications like that. Now, next is a really old application of electrolysis, and that is producing what would appear to be a silver spoon. But in fact, that spoon is mostly iron, or it may be more like steel. So iron with some other things. But they start out with a bar of silver, and that's where the oxidation is occurring. And then on the other side, they have a reduction where the cathode is, cathode being the spoon, and we're going to create a layer of silver on the outside of the iron spoon or the steel spoon. And again, it's electrolysis, so you see they have a voltage source here. And where this was used, maybe more than well, there was a lot of tableware produced this way. But one of the other applications of this is not with silver, but with chromium. And they would apply a layer of chromium and some other metals to automobile bumpers and other trim parts for the production of cars. And that was done for a long, long time because parts were made of steel, they would rust. You could paint them, but in some cases where they saw more impact with rocks and stuff like that, it would break through a paint layer. They would apply a chromium layer instead, and that would help it survive a little bit longer. And also it would look good. Now, nowadays, a lot of the parts you see that appear to be metal with a chrome layer on the outside are actually plastic. So that chrome, what looks like chrome trim is not. It's just really plastic. But I don't think there's a whole lot of chromed metal being produced nowadays. So in all of these electrolysis, what we're doing is we're taking, a cation of some sort, in this case a silver cation, and we're trying to make it into a solid. So that's what our next slide is about. Faraday's constant. This is, looking at what it takes to take a metal cation and make it into the metal. And I don't know why these don't have solid on there, but they should. Make it into the solid, like what we did there with silver. So we've got different cations that we're starting from. One is a 1 plus for A, the B is a 2 plus, the C is a 3 plus. And what we're seeing is it's going to take progressively more electrons in order to make it into the solid. So Faraday's constant is a way of quantifying how many electrons is it going to take. So here's the moles of electrons that were needed. And then we use Faraday's constant, converts it into coulombs. Coulombs is equal to 1 amp of electrical current for a time period of 1 second. So this is, we're basically calculating how much electricity would be required to do some of those processes that we saw earlier. And take home here is that the more positive the charge is, like C has the most positive charge, the more Faradays that would be required, more electrons would be required in order to reduce it to the metal. Now our next slide is taking two concepts that we had previously and joining them together with our electrochemistry. So first thing that we looked at this semester was equilibrium constants. And you remember that if K, say, were 100, well, that would be the same as saying that it is a fraction 100 over 1. And remembering that equilibrium constants, it's the product over the reactant. So what we're saying here in an equilibrium, oops, let's make that P into an R. There we go, reactants, and then process. And what we're saying here is that if K were 100 or 100 over 1, that it would favor the products and not the reactants. So we're going with this idea that if K is greater than 1, that also means it's a spontaneous process. And we're in electrochemistry chapter, so we would say, okay, that's a voltaic process. Now, we then went from equilibrium constants to Gibbs free energy, and that's down here. And for Gibbs free energy, we said that something is spontaneous if the Gibbs free energy is less than 0. So we're looking for a negative value. Okay, so what would correspond to spontaneous, or if we're thinking about it in terms of electrochemistry, voltaic, is if the Gibbs free energy is negative. So now we want to take these two here and relate them to each other, and we do that with this equation. And you saw this before, that there is a negative sign in the equation. So a positive large number for the equilibrium constant would then convert to a negative value for the Gibbs free energy. Now we are to the electrochemistry chapter. So now we're focused on a cell potential. And we said that for the process to be spontaneous or a voltaic cell, that this number needs to be greater than 0. So we're saying it needs to be positive to be spontaneous. So if we're comparing then the Gibbs free energy delta G to the cell potential. We have an equation that will do that. And the main thing about that equation is that there's a negative in there. So that changes the sign. So a negative Gibbs free energy that is spontaneous is going to go with a cell potential that is positive. So our negative is going to go to positive. And then finally, if we're wanting to relate the cell potential back to the equilibrium constant, we've got an equation that does that. Now you don't need to know these equations, and we're not going to calculate anything with them. We're just using that to get an understanding of how these numbers are related to each other. That you can see that if we take everything before the Q, or I mean before the K, I'm sorry. We took all that and rolled it all together, it would be a function, but it would not change the sign of K. So a positive cell potential is going to go with a positive value for K. So take home here, spontaneous, negative Gibbs free energy, positive cell potential, positive value for K, and it needs to be greater than 1. Okay, everybody got that? Anybody got a question? All righty, let's then, what we're going to do through the end here, let me see if that's true. We're going to look at some batteries. So that's an example of a voltaic cell. We're going to look at a fuel cell, which is different than a battery. And we'll talk about that, what that means. And then we'll be one more example of voltaic processes, spontaneous processes. We're going to be looking at corrosion, which is economically important, sort of boring, but it is important. So need to make you aware of that. So here we go, unless there is a question. Okay, not getting any questions, so we'll just keep going. So our first example of a battery is one of the very original products that was a result of experiments in electrochemistry, and that's the zinc carbon dry cell. And these were used for lighting, portable lighting. They were used in the earliest telephones because they did not have necessarily a electricity in the house, but they still had telephones. So anyway, for the zinc carbon cell, you're going to have, or dry cell, you're going to have a anode that is where the oxidation occurs, and that is this carbon rod. Then you have a cathode where you're going to have a reduction, and that is this combination of different solids, manganese oxide, ammonium chloride, zinc chloride, and that's in the form of a paste that surrounds, that's in here around the carbon electrode. So that was one application of electrochemistry. And the dry cells were important because everything that we were doing up to now, of hotels, you have to have a liquid in there. And that is not really great for a physical, a packaging, physical packaging of the whole thing, because you can have leaks. It may be that you have to keep the cells upright because they're not really sealed up. There's lots of restrictions Where with a dry cell, this thing can be in any orientation. It doesn't matter, turn it upside down, whatever. It still works. So this was an important development. We then went from the zinc carbon dry cell to the alkaline battery. These were the ones that were around for quite some. I mean, you can still buy these, of course, but you know, these were. This was a major improvement as far as what the weight was compared to the electrical potential you could produce. You know, we started out this chapter, we were looking at things like electric cars and cell phones, laptop computers, a lot of medical devices, things that cannot be heavy. If they're heavy, they're just not going to be useful. So this is the first improvement in reducing the weight to still get sufficient electrical potential. So again, we're going to have a cathode where you have the reduction. That's going to be manganese oxide powder mixed with coal dust or carbon. And then on the other side here, you're going to have the cathode and, excuse me, I'm sorry, I'm mixing things up here. Oh, let's just erase and start over again. Okay, we've got the cathode where we have the reduction, that's this powder, and then where we have our oxidation, which is the anode, they're calling it a current collector, and that is essentially a steel rod going up the middle of the packaging. Then our next jump forward in reducing weight and increasing our electrical current. So this is what this, there's a term that gets used in batteries. It's current density. It's how much electrical power can you have, you know, in the size of the package, and then it also gets into what the weight is. So anyway, with the NiCad batteries, those are rechargeable. You still have an oxidation reduction going on. You can see that it repeats. So you have anode, cathode, anode, cathode, anode, cathode, repeating back and forth. So this improves the packaging, increases the amount of electrical power, and reduces the weight and the size of the battery. And then the most recent development is the exploding lithium. No, not exploding. We don't want that to happen. But anyway, the lithium ion battery. And this is working on a little bit different principle. You don't really have moving electrons. Instead, you have moving electron holes, or it's the absence of an electron. So you can see that what is moving has a positive designation. You are moving the absence of an electron through the material. This all came about from the development of semiconductors. So prior to development of the transistor, these could not have been conceived really. But when we got into semiconductors, transistors, and then now we're at the point of, well, we've gone beyond integrated circuits now. We've gone to where it's packaged even smaller. But anyway, when we got to the idea of semiconductors, we could have this moving electron hole, and that's what produces our electrical current. So that is your lithium ion. Of course, those are rechargeable. And then now we're going to go way in reverse of the technology, and that is to the lead acid battery. Now, this is what you've got in your car. for your starter motor and to allow your lights and all your other stuff to work in your car. And these have been named for a long time. The technology has not improved a whole lot. They've come up with batteries that are sealed. You no longer would be adding water to the battery, but anyway, it's still pretty much the same thing. So you've got your anode, and that's going to be lead dioxide, and then your cathode is going to be lead. So you've got lead dioxide, and then we have a solution of sulfuric acid in there. And of course, these are definitely rechargeable. And I want to do a little safety thing here. Here's our positive terminal. Here's our negative terminal. If you go out and find that your automobile battery is dead, and you find someone that is willing to give you a jump on your battery, and you've got some jumper cables, I want to just real quick go through what you ought to do, because this process, it can be dangerous, because when you rapidly recharge a battery, you're going to produce some hydrogen gas. And hydrogen gas is flammable, it's explosive if you have the right combination of hydrogen gas to the oxygen in the surrounding air. So now you've got an exploding device that has sulfuric acid in there. That's not a great combination, because of course if you get the sulfuric acid in your face, you're going to have burns, you might be blinded, some bad things have happened. So we want to be careful about this. So the way to go about this is, first you make a connection with the jumper cable between the donor battery and your battery. So you connect the positive to the positive. Now make sure it is actually positive and positive. If you go positive and negative, you're going to destroy your battery and the other person's battery and maybe their charging system and all sorts of stuff. Also, you want to make sure that the donor battery's automobile is not running. You want it turned off. Okay? Then the next thing you're going to want to do is go from the donor battery's negative terminal, but not to the negative terminal on your car. You want to attach it to what is called a grounding point. So this symbol is representing that. In other words, you're looking for a bolt or a bare piece of metal on your car that you can clamp the cable to, and you want this to be away from, you want some separation between where you're making the connection and your battery, so that if it causes a spark, you don't ignite the hydrogen gas and you don't, get injured. At that point is when you can have the donor battery person turn it on. You guys are probably really laughing on that. Anyway, you turn, they start their car, let it run a while, leave this hooked up, and then when you're done, they ought to shut their car down. You ought to disconnect the cables and try to start your car, and not try to start it with the cable still connected. Okay, that's the safest approach. You could try to start it with the cables connected, but that is not as safe. Okay, main thing is to avoid connecting the negative from the donor battery directly to the negative on your battery as far as having a risk of having an explosion. So that's your safety message for the day, all the while maintaining social distancing somehow. Okay, let's now go to fuel cells. So the main thing about a fuel cell is that it's a continuous process. With a battery, it's, producing electricity until the battery is consumed. You could then recharge the battery in some cases, but while you're recharging it, you're not using it. Now, your automobile battery, it seems like you're doing both at the same time. You're really not exactly. If the car is running, the lights and everything are operating off of the alternator, not the battery. And when you're really using the battery, when you're starting the car, and then once it starts up, everything is running off the alternator. And then the alternator is recharging the battery, but you're not using the battery. So you cannot discharge and charge a battery at the same time. It's got to be one or the other. Excuse me. So a fuel cell is a different sort of thing. You don't have that, separate processes. With a fuel cell, as long as you're applying your fuel and your oxidizer, then it's going to produce electrical current. So in this example, our fuel is hydrogen gas and our oxidizer is oxygen. And this was one concept for a fuel cell operated automobile. Now, this is not a Tesla. This is not, because a Tesla has batteries. It's not producing electrical current with a fuel cell. But prior to all of that development, people were looking into fuel cells in automobiles and burning hydrogen gas. Now, that idea sort of went away because there's hydrogen. And they just realized that you could not trust the average person to refuel their automobile with hydrogen. And probably somebody would get blown up eventually. So that went away. Then what happened later on was they developed fuel cells that would burn methane, so CH4. And instead of using oxygen, well, even with the automobiles, they were actually not going to be using oxygen alone. They were going to be bringing in air and then using the oxygen air. They were going to be using air as their source of oxygen. But anyway, back to the methane or the CH4 with air. There has been a development of very large fuel cells that you could use at your home. Most of the time, this is for people that are living in remote areas and they want to produce electrical current for their home. So instead of using an electric generator that was not very efficient, they would use a fuel cell that is very efficient, and they would be burning methane or propane or some other fuel like that and using air that's present. And those work pretty well. And there's even a push that people could get these at their homes, not in remote areas where, more, like in the suburbs or maybe even the city, I don't know, but to produce electricity for their residents. And it could be cheaper than buying electricity, although that's been up and down and it has not, really taken hold. And then probably the oddest application of this was a concept for a fuel cell laptop computer. So with that one, they were going to use cartridges of ethanol. So that would be, they were going to have cartridges of ethanol, and they would use the oxygen that was in the air, and that would power your laptop computer. So instead of having to recharge your battery, or instead of looking for a place to plug in your laptop, you would just slap in a cartridge of ethanol and it would operate. But, you know, folks aren't real happy with the idea of having liquids around electronic devices, so it never really took hold. But it is a possible technology, and maybe in the future there might be a reason why this would be a great idea. I guess it would be good if you really don't have available electricity to plug into and your battery, even though your battery is going to go for a long time with the newest batteries, you know, there's still a limit. So it might become a viable idea again. Okay, so we're going to finish up here with talking about corrosion. So corrosion, you know, it's important. Not very interesting, really, but it's important because, you know, there's a lot of damage to property that occurs when you have corrosion. So it's important financially. And this would be things like the bridge structures, especially around Chicago. You know, we got a lot of rusting of bridge supports. When I was at NASA, we had a lot of concern with corrosion of the launch facilities. And in Florida, you know, it's really easy with the salt spray to get corrosion. So anyway, it's important from that idea. Now, what we're seeing here depicted is a piece of iron, or more likely it's going to be steel. And we're trying to protect it from corrosion. So our first defense is a layer of paint on the outside. And that will work until there is a hole in the paint. And it does not have to be a large hole. A small hole will suffice for that, because once this starts, it can then move under the surface of the paint. And if you're one of the folks that's blessed with an older automobile, then you probably know what I mean. You see that little dot of rust, you come back 3 months later, and now it has spread like cancer, consuming your automobile. So it only takes small holes in the paint layer for that to start happening. But anyway, what's going on there is you have to have some water present, which isn't a problem in Chicago or in Florida. And oxygen that's in the air is going to then, we're going to have a reduction with the water. The electricity that we're producing travels through the steel to another location where the iron in the steel is being converted to iron 2+, and that combines with oxygen, and then you're going to end up with iron oxide. So we're going to be getting FeO, or rust. So that's what you're seeing. But the biggest problem is you're making this hole here in the steel, and that just keeps getting bigger and bigger until finally the thing falls apart. So not a lot we can do about this on something like an automobile. They have started they apply layers of not chrome but zinc. They'll apply layers of zinc to the outside of the steel before they put the paint layer on, and then that makes it more resistant to rock impacts and things like that would start this whole process. Another strategy to protect some metal is cathodic protection. So we have an object to be protected, and then we bury in the vicinity of it a sacrificial anode, typically a piece of magnesium, and then we connect it with a wire so that electrons can flow. Oops, I'm getting a poor connection. I'm going to shut my camera off. Anyway, we get electron flow from the object being protected to the magnesium, and that causes this protective current it's talking about. And eventually, the sacrificial electrode will be gone. It will become magnesium cation, magnesium oxide. So you would have to replace the sacrificial electrode, every so often. And you may have noticed when stuck in traffic that some of the bridge structures will have a cable bolted to the side of the support and going to the ground, and that's what's going on. They have these sacrificial magnesium pieces that they're trying to use to protect the bridge structure, to cut down on the corrosion of that. So anyway, that's it on corrosion. That's it on electrochemistry. Anybody got a question on any of this stuff? Okay, it's super quiet. Okay, let's then go to our next chapter. So our next chapter is transition metals. This is a really short chapter. There is some sampling homework that goes with it. It's really short also. So here we go, transition metals and coordination chemistry. So this is chapter 19. And first off, we're going to talk about where transition metals come from, typically, or where they're found, and they would be present in minerals. And some of the minerals are, attractive. They could be gemstones. We have something called malachite that was used to produce paint back probably like 1400 or so. Azurite, same thing, producing paint from that. I'm not going to attempt to pronounce that one. I usually mess it up. But anyway, these are all minerals. Could be used as gemstones, have also been ground up into fine powder to be used in pigments. And in fact, our next slide is, well, what do we use this stuff for? Well, one of the oldest applications is pigments, also in gemstones in some cases. Transition metals can be used in catalyst for speeding up a chemical process, used in production of magnets. Some of the transition metals are found in biological molecules. They are present to facilitate transfer of electrons. And then they get used in organic synthesis. Sometimes if we're trying to produce a particular organic compound, usually for purposes of a medicine, we're trying to produce a molecule that's challenging to produce. We can use a transition metal catalyst there that will facilitate the production of that without it being quite so difficult to do. So transition metals, you recall periodic table, it's this area right here in the middle, and it is the D block elements. So we got scandium to zinc and all these other guys. So something that we need to consider here, it'll be on the next slide, is their oxidation numbers. Because if you have a S block element, like in the first two columns of the periodic table, these are either going to be only plus or 2 plus, right? You guys remember all that stuff. Then if you got aluminum right here, it's going to be 3 plus, and then after that you're out of the metals and you're to the non-metals, and that's a whole different story. But everything that is in this middle area here where the D block is, nearly most of those, I should say, most of those elements can have more than one oxidation state. So that's on this next slide. So something like manganese will have the most oxidation states. See, it can be 2 plus, 3 plus, 4 plus, 6 plus, 7 plus. It can do a lot of different oxidation states. And then as you go to either side away from that middle, you've got fewer oxidation states. So you got scandium out there with just 3 plus, you got zinc with just 2 plus. But things that are in the middle, manganese, chromium, iron, they're going to have a lot more oxidation states. And that's important in the way these function. And in biological processes and in other chemical processes. So we saw that our transition metals come in the form of minerals. This is pretty much the same thing. These are minerals also. Copper, gold, and iron. Except here, we're going to use these and we're going to melt them and we're going to refine them, because copper, gold, and iron all have financial value that we can use if we process them. Now, the other ones, the minerals, usually you don't process those. You just leave them in the combinations you found them, and they become gemstones or pigments. So these are examples of metal ores, and so now that's pretty much it on transition metals. Didn't have a lot to say there really, but we're going to go now to coordination chemistry. And what this slide is doing is it's showing us the difference in these 3 different types of bonding arrangements. So here we have covalent, so that would be CH4, also called methane. And the thing there is you're sharing electrons. Remember from Chem 140, we talked about every time you have a bond, you're sharing electrons. Then we have an example of an ionic compound, sodium chloride. And with sodium chloride, you've got ions. So the sodium loses electrons and becomes Na+. Chlorine electrons and becomes Cl negative. And then we're not sharing electrons to hold the molecule together. We have an attraction between opposite charges. So we've got an attraction between the positive. And in the case of covalent and ionic, there's some pretty easy rules to figure out what kind of formula you're going to end up with. For example, if we go to ionic, that's probably the easier one to see. Sodium chloride, it's 1-to-1, 1 sodium, 1 chlorine. If it were calcium chloride, CaCl2, you'd have 2 chlorines for every calcium because the calcium has 2 positive charges. And then over here for our CH4, we can draw a Lewis structure of that, and we can see how the electrons are being shared to hold that together. So for those two, it's pretty easy to figure out what the arrangement's going to look like. But when we get into coordination chemistry, things get a little weird. I don't know what else to say. They're just a little strong. Because we're starting out here in this case with our scandium 3+ cation. Now you may remember that we talked about stuff like this back in the equilibrium chapter, chapter 5. But we didn't really talk about what any of these things looked like. We just said, okay, these make these combinations of these molecules with a cation, and now you have a new cation that has some different properties as far as solubility goes and stuff like that. So, but what we're doing here is we're taking a scandium cation and we're combining it with 6 waters. And when we do that, we get this thing, this coordinate covalent compound. The water, and we're going to be using other things like this, those are called ligands. New term you need to remember, they're called ligands. Now what's weird about this is, how do you decide that it's going to be 6 waters with 1 scandium? Why isn't it 1 water? Why isn't it 2? Why isn't it 4? Why isn't it 8? Why is it 6? And it mostly comes from the shape of what can be produced. Or also it comes from the size. You know, how many waters can we fit around a scandium cation? So this kind of chemistry is a challenge for people. And I'll admit it's not one of my stronger areas either, because it is just really hard to see how you get how these would combine together. And don't worry, you're not going to have to be able to predict this, just be able to sort of understand what it looks like. Okay? So now we're going to go to 3 examples of some coordinate covalent complex ions. And this first one, this is the one that we talked about in chapter 5, where we have silver and we have ammonia with it. And the ammonia is the ligand. The silver started with 1 positive charge the complex ion still has one positive charge. Now, to sort of understand what this structure is looking like, you've got your nitrogen attached to 3 hydrogens. And remember, on these, there's a pair of lone pair electrons. So you've got some extra electrons. And then we have our silver with one positive charge. So we got some extra electrons on the nitrogen. We have a shortage of electrons on the silver. And that's what caused these to be attracted to each other, so that we can then get that coordinate covalent bond between them. Now the part that's weird is, well, we can do the same thing on the other side. But how do we justify that with only one positive charge? And it's really, it comes about because you can fit 2 ammonias around a silver. And so, since you can fit it in there, that's what gets produced. So the lone pair of electrons on the nitrogen, those go with the silver that is short 1 electron. So we have, in this case, we have 2 ligands, 2 ammonia molecules, and then we're going to start talking about something called contact points. The contact points are these lone pair electrons on the nitrogen in the ammonia. So we got 2 ligands. Each ligand has 1 contact point. So together we've got 2 contact points. Now, right now, why are we, talking about contact points? Why don't we just stick with the ligands? You'll see in just a moment why we need to do this. So for now, you'll just have to trust me on that one. Now, in this next one over, we've got copper, and I don't know why that says 2 negative. That is not right. That's supposed to be 2 plus. So, sorry, folks. That should really be 2 plus. Anyway, we got a copper cation, 2 plus, and to form this compound, we've got a bunch of chlorines, a bunch of chlorides. Now, I know you're thinking, well, why don't I just go UCl2? And you could, and that would be an ionic compound. But we can also get a complex ion that has 4 of these chlorides with it. And now we're going to be getting coordinate covalent bonds between them, where the copper is short by 2 electrons and each chloride has 1 additional electron. So that forms what we see here above it. We've got 4 ligands, 4 chlorides, and we've got 4 contact points because each chloride has those additional electrons. And then we're going to do one more here. We've got cobalt. I don't know if I'm going to be able to draw this whole thing in this small space, but anyway. The cobalt comes in as cobalt 2 plus. I'm just going to show 1 water. I think it's going to be too hard to draw more than that. Here's a water molecule. And hopefully you recall that the oxygen on the water has 2 pairs of lone pair electrons. So one of those could form a coordinate covalent bond with the cobalt. Now you notice that you got 6 ligands, 6 water molecules, and each water molecule has a pair of electrons that are available. Now it actually has 2 pair, but because of the geometry, only one of those pairs is going to be available to use. So that's going to give you 6 contact points. Now I want to look at this next slide, and then I'm going to cut you guys loose. Here's an example of a molecule to where you have 1 ligand but that 1 ligand has 2 contact points. One is the pair of electrons on that nitrogen, and one is the pair of electrons on the other nitrogen. So that you can form this coordinate covalent complex ion using cobalt. This 3 plus, and we've got 1, 2, 3 of the molecule that's on the left here. So that gives you 3 ligands. If you take the molecule that's on the left and you just rotate the nitrogens around, it will look like one of these. So there is 1, 2, and 3 of those. So we have 3 ligands, but each ligand has 2 contact points. So 3 times 2 gives me 6 contact points. So now going back to the previous slide for a moment, we can see that you can have 6 contact points. They can come from 6 ligands, or as we see over here, they can come from 3 ligands. So what really matters is the number of contact points, not the number of ligands. So what we're going to see going forward, we're going to just start falling into this pattern. You're either going to have 2 contact points, you're going to have 4 contact points, or you're going to have 6 contact points. Those contact points can come from 2 ligands, 4 ligands, 6 ligands, or like we're seeing over here, can come from 3 ligands. Okay, I'm going to wish you guys a good remainder of your day as best you can in our current situation. Be safe, take care of each other, and I'll see you guys on Friday. If you need anything, please contact me, okay? Especially with the sapling access, if you're having any issues there, please contact me right away. So I'll see you on Friday. Yeah, take care, Yulia. And Clarissa, and all you guys, Areli, all of you, take care.